the only course which I think I like is this.
It's really fun.
This is fun actually.
Yeah.
Yeah.
It's kind of hard though, because it's not like here's the equation or here's the equation, just plug in.
But this one is a little
You gotta think
bit
about it.
direct. It's not like
Calculus though.
not like calculus. Yeah. It's not like-
Well, the hardest thing on calculus is the algebra to organize the functions so then you can do the simple derivation. Like,
derivation.
you have 7 rules, like these are the only things you could do.
Yeah.
You know, it's like getting the formula there. Here it's pretty direct, but like I've done matrices before in previous math classes, so it's like, okay, I'm coming back to this like familiar like framework, and now we're just kind of focusing in on it and keeping it organized though, I think is like probably the biggest challenge that I could anticipate from this class.
Yeah, this class is actually applicable in I think in all areas like engineering, computer science, because if you do computer science actually, and if you focus on neural networks, machine learning, this is what you need. So you will need linear algebra to do all those stuff. So most of the people, they usually ignore it, but it is actually so important, even in engineering, because once you do your project, then when you're doing your analysis, you put some stuff in matrices, and then you put the analysis in either coding or something like that, and then you produce the results. Even statistics itself, they use linear algebra. Yeah. Okay, let's see how we will. So I want us to go back to 1.9, which I think we did it, but we did not finish it. So basically what we had just done is just the standard basic vectors, which are E1, E2, E3, and then when you put it in a matrix form, then it forms the identity matrix there. Forms the identity matrix. And then when you're given this one and this one, and then you're told to write just standard matrix. So you came with your lunch, eh?
What did you say?
So you came with your lunch.
I just ran over here. I like not paying attention. Yeah, I brought lunch. No.
Okay, so if you're given this kind of so this is actually the image just from here. Then to write the standard matrix, then you use this as the standard matrix. So you just put it like this. So this is the standard matrix. The standard matrix. Okay, so we did up to there in section 1.9. Now, I want us to now go to which the section which I said we will do it, which is the onto and 1-to-1 transformations. Onto and 1-to-1 transformations. Okay, let's start from the, so onto most of the time, most of the people, they use the surjective. And this one is injective. That is what most of the people use in subjectivity. So let's start from the first one, which is onto, or the surjective. A transformation which we put it as from Rn to Rm. is onto if for each vector B in Rm, there is at least one vector X in Rn such that T of X equals to B, which we usually name this one as M of T equals to Rm. M of T equals to Rm. So when you say at least, there is something which, if you have this one over there, this is Rm, this one is Rm. We have this transformation here. So there is some vectors, there are some vectors there, B. So you want us to smell your food there?
Color arrow.
So there is, so what kind of food do you like? So what is that?
I like all food.
So
This is Mexican food.
what is inside that?
It's just a steak burrito from El Heredero, Mexican food.
Oh, with some beef or something?
Steak,
Oh, steak.
grilled steak, carne asada.
I usually like cooking for myself.
I love cooking for myself. It's just, I don't have a whole thing.
Yeah.
So like, so yesterday I left my house at 6 and I got home at 10.
Oh, 6 a.m. in the morning.
Yeah, and got home at 10 at night. So
Long day.
yeah.
Your name is Scott, right?
Yes.
Oh,
And yesterday, the only thing I ate until I got home was breakfast. Same thing the day before. I'm like, oh, it's kicking my butt.
yeah. So if we have these elements here in B, there is at least some vectors here, X. There's some at least something here, which can actually map. So you can have as many elements here, but there should be maps. So there is this which can map to any of them there. Okay.
I have a quick question. What did that, like, specifically, what do you mean by it can map over, like, functionality? Like, what does it mean to?
Yeah, so if we have the vectors in here, so it says if it is onto, then the vectors B in Rm, which is here, so there is at least one vector which is here, at least one vector which is here, which can actually, so any element here, let's say we have vector B1 here, and another one here, maybe B2 here, and these are vectors. So, and let's say we have only one here, let's say X1 here, okay? So this can actually take that and also can pick that one.
Okay, so through a function, like multiply through a matrix and.
Yes, so
Put out
in
this
this place here, then it will be T of X1 equals to B1. T of X2 of X1 again can also be equals to B1. Okay, can also be equals to B1. So it takes, so any vector which is one vector here can have any vector which is here. It can map here. So any vector. We'll see one-to-one. One-to-one should be what you have here should map directly to one here. It should not be like one taking two of them here. So it should actually be 1-to-1.
Okay.
This one to this to this, another one to that. Should not be like this. Should not be sharing like that. So it should be 1-to-1.
Yeah, and onto and later.
Yeah, so for onto there is at least. For 1-to-1 it is at most. So it is at most. So this one is at least.
Okay.
At least Yeah. Okay. Let's look at theorem 2.2 theorem. So what happens when it is now a matrix? So when you form a matrix from here, what can we say about for it to be onto? Okay, so we can write if we let A be the standard. Here we're talking about the standard matrix of a linear transformation. T from Rn all the way to Rm. Then T is onto if and only if every row of A has a pivot position. Every row of A has a pivot position. So for this one to be onto, so the standard matrix, then every row of A should have a pivot position. So it doesn't matter. So it can be two matrices like this. So every row here, let's say that is 1, that is 0, let's say 2 and the rest there, and let's say 2 here. So it should have a pivot position in each row. Then this one is onto. So again, it doesn't matter whether it is 3 by 3, 4 by 4, or something like that. As long as every row has a pivot position, then it is onto. So we can also have the free variables there. So you can also have free variables. It doesn't matter as long as every row has a pivot position. Okay, so we can prove these. Let's prove this one first. If we write A to be equals to A1, A2, all the way to AN, where A1, A2, all the way to AN are in Rm. If these ones are in Rm, then the image, because we said for this one to be onto, then the image is what? Rm. The image of T equals to, and we said last time, image of T is equals to T of X, whereby X is an element of Rn. X is an element of Rn. And how can we write this? We can also write this as T of X is equals to what? Ax, whereby also X is equals to X1, X2, all the way to Xn. And these are also in what? Rn. Also Rn. And since A is this, one, then this is equals to A1, A2, all the way to AN. And this will be X equals to, this is like this. Yeah, this is like this, whereby X is an element of what? And this can also be written by, you can now multiply this, which is A1, no, X1 A1 plus Xn AN. whereby now x1 all the way to xn are elements of real numbers. So these are the values which we will be looking for. So therefore, if we still remember this can be written as the span of what? The span of, since this one is a linear combination, the span of A1 all the way to the span of A. Span of A1 all the way to the span of A. So therefore, the range of T is the subspace of Rm spanned by A1 all the way to A1 all the way to AN. And that's it. That is how you can prove that. So then T is onto if and only if the columns of A span Rm, if and only if every row of A has a pivot position. That's a pivot position. So that is, so the main thing that we need to remember is every row position. Okay, let's look at the first example in this. It will be example number 2. Let's look at the first thing. 2. If we let's T from R3 to R2 be a linear transformation defined by T of x1, x2, and x3, which is equals to x1 minus x2 plus x3, x1 plus x2 plus x3 for x1, x2, x3 elements of R3. Now, is T onto? Is T onto? Now, we said that for this one to be onto, for T to be onto, then we let A to be the standard matrix. So here we need to get the standard matrix here. And the standard matrix, we said the standard matrix of A solution. For A to be the standard matrix, then it is, in our case here, then it is T of E1, T of E2, and what? T of E3. That is our standard matrix. Now, we know that E1 in our case is what? So is that it is, in this case, it is how many of them? 1, 2, 3, right? So E1 will be 1, 0, 0. E2 will be 0, 1, 0. And then E3 would be 0, 0, and 1, and 1. And 1. Now, to now get T of E1, then we know that x1 here is x1, x2 is 0, and x3 is what? Is 0. So we now bring it here. So x1 is 1, and then the others are zeros. So T of E1 will be what? 1, and then all these are the zeros, and then this one is also 1. Okay? Are we together up to that? So this is x1, x2, and x3. x1, x2, x3. x1 here is 1. The others are zeros. So when you come and represent it here, then it is 1, and then all these are zeros, 1, and then all these are zeros. So we have T of E1 is 1, 1. T of E2 is now equals to, this is 0, 1, 0. So x2 is 1. x2 is 1. So it is, here it is -1, and then x2 here is 1. So it is 1 there. And then finally, T of E3 is equals to, the last one, x3 is 1. So 1, and then here is 1. There is 1. Okay. So our standard matrix, now we represent it here, is now, or A equals to 1, 1, -1, 1, and then 1, 1. So that is our standard matrix. Then for this now to be onto, then we need to reduce this, and we need to show if all the rows have the what? Pivot positions. So we reduce this one. So our new R2 will be R2 minus R1, which we get 1, -1, 1, 0, 2, and 0. So looking at that, we have the pivot positions in each of the row. So this means that every row of A has pivot position. So T is 1, 2. T is 1, 2. Any question after that? Okay, if there is no question, then let's look at another theorem, the definition here, and this is 1-to-1. Definition 2.3. A transformation T from Rn to Rn is 1-to-1, 1-to-1. If for each vector B in Rn, sorry, there is at most one vector X in Rn such that T of X equals to B, which you can name this one as, namely Tu equals to Tv, and this can also be U equals to B. So this is different on, and this is, it is actually 1-to-1 matching. So it is mapping from one to the other. They are not shared, so they are not shared. So T of U, the transformation, if you have an then U can be equals to if we let A be the standard matrix of linear transformation, which is T from Rn all the way to Rm. Then T is 1 to 1. If and only if Ax equals to 0 vector. If and only if Ax equals to 0 vector. That means Ax equals to 0 vector has trivial solutions. So it means that each column here has a pivot position. Each column has a pivot position. So it means this A and 0 vector there. This first, the columns in A here should all of them have the pivot positions. They should have the pivot positions. This is the argumented matrix. So this A here, all of this here, each of the columns should have a pivot position. For this one to have a trivial, for it to have a trivial solution. So for it to be 1 to 1, then A of x equals to 0 has trivial solutions.
No free variables, right?
Yes, no free variable for this to be 1 to 1. No free variable. Okay, you could look at your book for the proof of that. I think it's there. I don't want to take a lot of time proving.
Iron proof. We believe you.
I know you guys. I know you guys don't like proofs. I mean, I don't like.
Sometimes I do, not most of them. though.
I don't like. Okay. Another theorem, theorem 2.5. If we let A be the standard of a linear transformation, from of T from Rn all the way to Rm, then T is 1 to 1 if and only if every column of A has a pivot position. Every column A has pivot position. Pivot position. Okay, I want us to write a proof of this because this proof can summarize most of the things that we have actually done. So let's write a proof of this one. So let's prove this. If we let T of x to be equals to Ax for x, which is in Rn, for x, which is in Rn, then T is 1 to 1. T is 1 to 1 if and only if Ax equals to 1, equals to 0, 0 equals to 0. Has what? Has trivial solutions. only. Has trivial solutions only. And this also means that all variables in AX equals to 0 are what? Are the basic variables. Are the basic variables. It also means that the first n columns of A and 0, which is the augmented matrix, are the pivot. And also this is means every column of A has pivot positions. So it's just summarizing what we just said. Okay, let's look at an example. Just example number 3. We let T to be from R3 all the way to R3 be the linear transformation. We have T of E1 to be equals to 1, 2, and 4. T of E2 to be equals to 1, 1, and 2. And then T of E3 to be equals to 0, 3, and 6. Then is T 1, 2, 1 is T1, 2. So we need to write that in standard matrix, and the standard matrix is, so the solution. So the standard matrix is A equals to T of E1, T of E2, and then T of E3, which is equals to 1, 2, 4, 1, 1, 2, 0, 3, and 6. So that is our standard matrix. And then we do what? And then we reduce this to see whether each of the columns will give us the pivot position. So when we reduce this, then we go home and reduce to echelon form. Then what you get is 1, 1, 0, 0, negative 1, 3, and 0, 0, or 3. That is what you will get. So looking at this, we don't have any position. So it means this is not 1, 2, 1. So the third column of A does not have pivot position. So T is not 1, 2, 1. T is not 1, 2. It is not also onto, because the last row here doesn't have the pivot position. Example number 4. We let T from R3 all the way to also R3 be the linear transformation such that T of E1 equals to 1, 2, 4. T of E2 equals to 1, 1, 2. And T of E3 equals to 0, 3, and 9. similar to the first one there, but we've changed the last entry here to be 9. Is T 1 to 1? So you just put the standard matrix, which is 1, 2, 4, 1, 1, 2, 0, 3, 9. So when you reduce this to echelon form, then what you get is 1, 1, 0, 0, negative 1, 3, 0, 0, and 3 there. This has a pivot position in each of the columns. So T is 1, 2, 1. T is 1, 2, 1. And that is it. That is it. And
I've got a quick question.
Mhm.
Since there's a pivot position in every column and there's also one in every row, would that mean that 1-to-1 transformations are also onto transformations?
yeah, it can be onto, and that we usually call it bijective. It can be 1-to-1 and onto. So we call it bijective.
Okay.
Yeah, so this is 1-to-1 and it's also onto. So it's basically bijective. Yep.
Yeah.
Okay, now let's now come to the next chapter, which is 2. And we will start from 2.1. Yep. The first example just be chapter 1.
Right.
So don't worry about it. Step down, chapter 1. So we'll start from, this is the easiest chapter actually. Very easy. The one which I don't like so much is chapter 4. It's more of a lot of theorems, so we'll prove a lot of theorems.
Chapter 1, a lot of theorems.
Yeah, chapter 1 doesn't have a lot of it. Chapter
Seems like it.
4 is the one which is a little bit crazy.
A lot of them were real simple theorems.
Yeah, this one is the easiest actually.
Cool.
So chapter 2. So 2.1, we have the matrix operation. The matrix operations. And we will start from the first one, which is the addition and scale multiplication for matrices. And I know most of you are familiar with this, so it's not so much difficult. Definition. We let A and B be M by N matrices, and R be a number. Then if A equals to A11, A12, all the way to A1N, A21, A22, all the way to A2N, AM1, AM2, all the way to AMN. So this is basically an M by N matrix. And if we have our B to be B11, B12, all the way to B1N, B21, B22, all the way to B2N, and then BN1, M1, BM2, all the way to BMN. Then the matrix addition, A plus B equals to, so we basically adding the entries there. Since this is an M by N, then we add the entries here. So A11 plus B11, A12 plus B12, all the way to A1n plus B1n, A21 plus B21, A22 plus B22, all the way to A1n, A2n plus B2n. Same thing, AM1 plus BM1, AM2 plus BM2, all the way to AMN plus BMN. So that is the addition. Now, if we multiply by R, scalar multiplication, which we can take R and A, then it is similar to R A11, R A12, R A1n, R A21, R A22, R A2n, R AM1, R AM2, R AM. So that is how you can multiply by the scalar multiple. Now, the remark. Number one, the negative matrix of A is defined by negative A, which is the same as -1 and A. That is a negative. Number two, the matrix subtraction is defined as or by A minus B, which is the same as A plus -1. So we can define that. And then lastly, number three, we usually use 0 to denote zero matrix, where all the entries are what? Others, all the entries. Okay. Now let's look at the examples on how to add the matrices and multiply by the scalar, which is very simple. So example number one. Example number one. Right in the next page. Find 2A minus 3B, where A equals to 2, 0, minus 1, 4, minus 5, and 2, and B equals to 7, minus 5, and 1, 1, minus 4, and minus 3. So it's combining scalar multiplication and addition. So 2A minus 3B is the same as 2, 0, minus 1, 4, minus 5, 2, minus 3, 7, minus 5, 1, 0, minus 4, minus 3. This is equals to, we distribute 2 inside there, which is equals to 4, 0, minus 2, 8, minus 10, 4, minus 21, minus 15, 3, 0, minus 12, minus 9. And what you get is 4 minus 21, 0 minus 15, minus 2 minus 3, 8 minus 0, minus 10 minus 12, and then 4 minus 9, or minus 9. Finally, what do you get? Minus 17, 15, minus 5, 8, minus.
Should, I think it should be 8 minus 3.
8 minus 3, right?
Yeah.
I'm doing my own things.
The first
Oh,
row.
this is
Yeah,
1.
that's a 1.
So this would be 3. So this is 5. And this one should be.
Minus 12. Minus 12.
So minus 12. So plus 12. This is 2. And then this is 13. That is 13. So that is how you can add and multiply by the scalar. Okay, let's look at the properties. So properties of this scalar and matrix addition. We let A, B, and C be matrices of the same dimensions. And RS be numbers. So just the way we were adding the vectors, so it is similar to this matrix. So the first one is number A, commutativity. We have two matrices A plus B. It is the same as B plus what? A. So that is commutative. B, if we have A plus B plus C, it is the same as A plus B plus C. So we can actually add A plus B. It is equals to adding B plus C and then adding A. But C, A plus 0. And this is an identity for addition. And this is 0 matrix. It is the same as what? A. But C, A plus minus A is the same as what? 0. And then number D, R, A plus B, it is the same as distributing R, A plus what? R, B. Then number E, R plus S, and then we have our A is the same as R, A plus S, A. Then number E, G, R, S, A is the same as multiplying RS, and then you multiply by A. And then number H, when you have the identity multiplied by A, it is the same as what? A. So these properties are just the same as the ones we had in the vectors. Okay, now let's come to the next section, which is multiplication. Number 2. Multiplication of matrices. So there are some properties which you must know before you multiply a matrix. Okay, I will let me use a sketch before we multiply this. So if we have this, that one, and that, okay. If we have this matrix here, we can take this one as Rn and this one as R. Yeah, there. Then we have this as, we can take this one as Rp. Rp there. So we said this is a transformation. If we can take this one as what? T, right? That is what we have been using frequently. We can take this one as S here. We can take that as S. Now, this is actually the same as if we take this as we have the elements here as X, then the transformation here will be what? T of X. T of X, which is similar to what? AX, right? Which is similar to AX. Now, if we take this one as Y, at this point we have Y. Then to transform to this point, then it is what? SY. SY. And this SY is equals to what? Is equals to X. And this SY also is equals to what? BY, right? Equals to BY. So we can take it like that. Now, the multiplication now of A and B, A multiplied by B is the same as T of S. T of S. Okay. So we are actually composing. It's a composite of this is B. This section and this is A. Then when you multiply A and B, then it is like composing of T. It's actually for okay. So then T of S of X T of S of X, okay. T of S of X is the same as T of S of X there, which is like that. Okay, which is like that. So it is like that. So it is the same as actually multiplying A and is like multiplying A and B of X. So basically, this is like you multiply A and B. You multiply A and B. So that was a sketch. Now let's write this definition here to see if it is making some sense. 2.1 definition. If we let A be an M by N matrix and B be an N by P matrix. N by P matrix. Define T to be from Rn to Rn by T of Y. We actually interchange to be equals to A of Y. T of Y to be equals to A of Y. Okay, to be that. For Y to be in Rn, for Y to be in Rn. And if we take S to be from Rp all the way to Rn, from Rp all the way to Rn by Sx equals to Px. Sx equals to Px. For X element of Rp, for X element of Rp, then both S and T are linear transformation. Both linear transformation. The composite of S and T is also linear transformation. It's also linear transformation. And this is like T of S, which is from, in this case, from Rp all the way to Rm, from Rp all the way to Rm. T of S is from Rp to Rm. And in this case, for X, which is in what? Rp. For X, which is in Rp. And therefore, T of S of X is similar to T of S of X. Okay, is similar to that. So it is similar to that. And we said this S of X is what? So T of B of X. T of B of X. And T of So this is T of B of X. Yeah. I'm trying to relate to this. Okay, so anyway, it is like this. So the standard matrix T of S, which is written AB. So we write as AB is called the matrix multiplication of A by B, which is M by P matrix, which is M by P matrix. So here, what it means is the number of rows or the number of columns in A should be equal to the number of rows in B for this matrix to be defined, for this one to be defined. And we can write a remark here. The matrix product AB is defined only if the number of columns of A is equal to the number of rows in B. So they will only be defined if the number of columns or the number of rows in A should be equal. The number of columns in A should be equal to the number of rows in B. And we can write this like this. We can write this if we let B to be equals to B1, B2, all the way to B, and let X to be equals to X1 all the way to XP, and these are elements of RP. These are elements of RP. Then T of S of X is equals to T of S of X there. And we say this S of X is the same as BX. Is the same as BX. And this BX here is this. So, and then we multiply by X here. So it is T of X1 B1 plus X2 B2 plus, you continue like that, X P T B P. Let's take this one to be P. Okay. So XP BP there. Okay. Now, if we now distribute this T here, then it is the same as X1 T of B1 plus X2 T of B2 plus XP T of BP there. And in a standard, if we put this one in matrix form, then this is like T of B1. And you continue like that, T of BP there. And then we put here one X, put there X, okay. And this is the same as, since this T is the same as A, so it is the same as A, B1, and then all the way. So it is this matrix here, and then A, BP there, and then X, and then X. So you multiply the matrix by the vector in B, the matrix A by the vector in B also. So it is similar to that. So AB is equals to AB1 all the way to ABP. So that is how you can multiply the matrix. Okay, let's see an example on how we can multiply the matrices. So example number 2, if we let A to be equals to 1, 2, minus 2, and 1, and B equals to 2, 0, minus 1, 4, minus 5, and 2. Find AB and BA. Find AB. So AB solution. So AB is equals to 1, 2, minus 2, 1. And then B is 2, 0, minus 1, 4, minus 5, and 2. So using this, we take this one as B1, B2, and B3 here. Then if you use this one, then the first column here, first column will now be A, B1, which is the same as 1, 2, minus 2, 1. B1 is 2, 4. Okay. A, B2, which is equals to 1, 2, minus 2, 1, multiplied by 0, minus 5. We get that. And then A, B3 equals to 1, 2, minus 2, 1, multiplied by the last one there, minus 1, 2. Multiply the way we did in the vectors. So the first one which you get here is equals to, so this and this is 2, so this is 10, and that, and this is what? 0. The next one there is minus 10 and minus 5. And then the last one there is 3 and 4. Therefore, AB equals to, we now combine those ones, 10, 0, minus 10, minus 5, and 3 and 4. 3 and 4. So that is how you can multiply the matrices. So in this case, it is defined because the number of columns in A are equals to the number of rows in B. Now, what about BA? BA, if you look at the number of columns here, they are not equals to the number of rows in A. So BA is, or we can say, the matrix product. BA is undefined. Is undefined. Matrix product. So this is one way of multiplying the matrices. So you take A multiplied by the columns in B, A multiplied by this, A multiplied by that. Into that. Another way of solving this is by use of row column rule, which we also did this one in vectors. The row column rule. Just still the same thing with our vectors. So if A is an M by N matrix, and B is an N by P matrix, then the I and J entry in the matrix product AB is given by AI1 B1J plus AI2 B2J plus AIN BNJ, which is the same as the summation of K equals to 1 to N AIK BKJ, where I equals to 1 to all the way to N and J equals to 1 to all the way to P. All the way to P. So you take the row and then the column in between. Okay, take the row and then the column. So you multiply the first entry, let's say 1, 1. So you take 1 and JS1. First entry and the first entry in V plus second entry to, let's say 1. We're taking 1. We use 1, 1, 1. So it is 1, A1, 1, A1, 2, A1, N. So it's the row and then the row. Then J is B1, 1, B1, and then B2, 1, which is down. So you're going like that. Okay, for example, still have like 2 minutes. For example, if we, example number 3, find AB where A equals to 0, 2, 1, 3, minus 1, 4. Then B equals to 2, 3, 1, 1 minus 1, 2. So if we want to multiply this, so it's AB, which is equals to 0, 2, 1, 3, minus 1, 4, multiplied by 2, 3, 1, 1, minus 1, 2. So this is the same as 0 and 2, so 0 multiplied by 2 plus 2 multiplied by 1, 2 multiplied by 1. That is the first entry. The next one is take that and that, take that and that. 0 multiplied by 3 plus 2 multiplied by negative 1. The next one is 0 multiplied by 1 plus 2 multiplied by 2. Go to the next, take this and the first column there. 1 multiplied by 2 plus 3 multiplied by 1. The next one, this and that. 1 multiplied by 3 plus minus 1 multiplied by 3. Take that and that. 1 multiplied by 1 plus 3 multiplied by 2. Same one, the last one. Minus 1 multiplied by 2 plus 4 multiplied by 1. The next one is minus 1 multiplied by 3 plus 4 multiplied by negative 1. And then the last one, 1 multiplied by 1 plus 4 multiplied by 2. So that is how you do it. So you pick this and that. So that is the first entry. Pick the next one and that. Second one. Pick the last one and that. The third one. Pick this and the first, like that and that till the end. So what you get here is 2 minus 2, 4, 5, 0, and 7, and then 2 minus 7, and 7. So that is what you should get. Any question after that? Okay, you guys have a nice long weekend. So I will try all I can to post the practice exam by tomorrow. Yeah.
Good.
Okay, I will see you on Tuesday.
Yes. Tuesday.
So I'll pause some of the homeworks today. That's right.
There are more.
Yeah, I will add some more for this section 1.9.
Yes. Still have 1.8 still up there.
Did you add more questions to it, or is it just a third question?
I'll add some more questions on 1.9.
Just
I haven't put any questions for 1.9. So it's just we haven't covered too much. Oh, we have finished 1.9. Okay, so I'll put more questions on 1.9. I might not put for 2.1. 2.1 I can put it next week.
Cool. Sounds good.
All right,
Thank you.
see you.